The truth is, hypothesis testing is very, very simple to understand, but in order to understand it and do well, you have to cover all this material in front of it and really understand all of those concepts. Otherwise, the whole concept of hypothesis testing doesn't make sense. So what we're actually going to start this batch of lessons off before we get to any hypothesis testing is we're going to be talking about confidence intervals involving population proportions. Now, if you remember back to the previous volume of Mastering Statistics, we covered confidence intervals in great detail. Mostly what we were concerning ourselves with was the population or the confidence interval of population means. And so if you've never watched that material, if you've never watched the previous information on confidence intervals, you really need to stop everything you're doing right now, go back and get that material and watch. Most importantly, learn and understand all of that material because it's all building. Everything we're going to do here is going to kind of assume that you understand that, and hypothesis testing in turn is going to assume that you understand confidence intervals. The two concepts are not that far apart. Especially how we use the normal distribution, the t-distribution, and we're also going to learn some other distributions. But they're very similar how you handle it for confidence intervals as to how you handle it when you do hypothesis testing. Okay, so here we're going to talk about confidence intervals with population proportions. And so I want to remind you briefly, just a real quick sentence or two, what a confidence interval is what we've done in the past. So just to remind you, what it basically is we have a population out there. You know, we want to understand the mean of that population. Could be the mean of their IQ, could be the mean of their heights, could be the mean of any parameter associated with the population. Well, clearly we can't go to the whole population and measure everybody's height or everybody's IQ. That would be millions of people. So what we do instead is we take a sample. So we may sample 50 people or 40 people or 69 people or something like this. And we look at the sample data that we get, and we look at, if we're studying heights, for instance, we look at how high these people are. We have 59 measurements or something, which is our sample of the population. So we can get in a mean of our samples, right? And we think that's pretty good representation of the population mean, but clearly it's not totally exact because we're only taking a small sample. The population's enormous, right? Obviously, the larger the number of samples, the better. But let's say we have like 100 samples or 95 samples, and we get an average height or an average IQ or whatever it is we're studying. Okay, how can we use that information and estimate what the population mean is for the average IQ of the whole country, let's say? Let's say that's our population we're studying. Well, we know that our sample mean is not going to be exactly the same as the population mean, but it should be pretty close. So what we do is we come up with this idea called a confidence interval. It's basically a fudge factor that we basically look at our sample mean that we get from our measured data, and we say, okay, that's going to be in the middle of the window. Now there's some error associated with that, plus and minus our sample mean, and that error is called the margin of error. And so once we know what the margin of error is that we can calculate this window by adding and subtracting from the sample mean that we have. We get a window, and then we say that the population mean, which could be the population IQ or the population heights or whatever, is going to fall within this window with a certain level of confidence. Level of confidence comes and plays into everything with these margins of error and these confidence intervals. Also, the level of confidence comes into play significantly in hypothesis testing. But in any case, so far what we've done is problems associated with the population mean and the sample mean. And if you remember, we had two main cases. We had a large number of samples. That means the sample data that we get is 30 or greater. And then we have a small sample size, which means less than 30. All right? And if you remember back from the previous lessons, and you should have already watched those, if we have a large number of samples, we use the normal distribution to calculate the confidence interval. And if we have a smaller sample size than 30, we call it small samples, then we use what we call the t-distribution. Now the normal distribution is bell-shaped, and the t-distribution is also bell-shaped, but the exact shape of the t-distribution is slightly steeper or fatter, but it definitely is still bell-shaped and it's still symmetrical. I'm telling you all of this because we're going to march on into some new territory here, and also in the back of your mind I want you to also be thinking that similar techniques are going to be used for hypothesis testing. So later on when we get to hypothesis testing, we're going to have small samples and large samples, and we'll be using either the normal distribution or the t-distribution, and in some cases a different distribution that we'll talk about later as well. So there's a lot of parallel stuff going on here between confidence intervals and hypothesis testing, so don't forget this stuff once you do it. All right, so backing up the truck, we've done confidence intervals for means with small samples and large samples. Now we're going to do a confidence interval for population proportions. Now, what do you remember about the word proportion? We've talked about it many times. The proportion is the fraction of population that has a characteristic. So it's a fraction. We usually express it as a percentage of the population. I'm just going to say fraction of the population that has some characteristics. So for instance, it could be 10% of males like books. This is just a proportion. So if you're talking about the entire population, it would be 10% of all males in the population like books, and so on. And we denote this proportion, we denote it with just a lowercase p. That means the population proportion. All right, now this is the proportion of a large group of people called a population, but we can never really measure everyone in the population. So we really talk about sample proportions a lot. And that's exactly what it sounds like. We have a sample proportion. What a sample proportion is, it's a proportion, I'm going to say proportion, for a sample of size n. Sample size is usually called n. So let's say I can't look at everybody in the country and see what percentage of people like books, but I can go sample 50 people. Then in that case, my sample size would be 50, and my sample proportion is whatever measurement I get from that. Maybe 2 out of 50 people or 6 out of 50 people tell me that they like books, and so I can represent that as a percentage, and that would be called the sample proportion. Now, in order to differentiate if you're talking about the sample proportion or the population proportion, this is denoted lowercase p with a hat on top. And we probably talked about that before at some point too. That you need to understand the difference here. When you see a hat on top, you automatically know that that's talking about sampled data. It's probably 30, 40, 50, 60 samples, but it's the measurement that comes from your surveying. When you don't have any hat like that, this is talking about the whole population. We can't really measure that, but we know that it exists, okay? Now, just like before, we have a margin of error, like we always have, and the margin of error really plays exactly the same role as it's done in all of the problems that we've done so far. If you remember before when we did the previous confidence intervals, I gave you an equation for the margin of error for the mean. So we look at our sample mean and we add a margin of error and we subtract a margin of error. Same exact concept is going to be here. I'm going to switch colors to hopefully make it a little more clear. The margin of error here is going to be equal to z sub c, which is a critical value of z because we're going to be using a normal distribution, and that's times the square root of p hat 1 minus p hat over the sample size n. Now, we're going to be doing a lot of different cases in statistics here in the confidence interval area and in the hypothesis testing area. And I'm going to be throwing these equations at you a lot. When you see an equation like that, you should not think to yourself that you understand where that equation necessarily comes from, because we haven't derived this equation. We haven't done any math to show you why this is true. When you get into an introductory statistics class, you kind of have to assume that people before you have discovered these things and proved them to be true. Your job is just to understand how they work, understand the limitations, and understand how to use them. When you get to more advanced statistics courses, if you go down that road, then you'll be proving that this thing is true. You'll be understanding why is the margin of error equal to this specific equation. There's got to be a reason. Somebody didn't just make it up. But we're not deriving that stuff here. We're not getting into those details because it's not really fruitful. But what you need to know is that the margin of error to construct a confidence interval of a proportion is equal to some critical value of z. We'll talk about that in a minute. And then here is the measured data that we have. P hat comes from the sampling that we do. 1 minus p hat comes from the sampling that we do. N is just the number of samples that we have. So 50 samples, 65 samples, 100 people. These are the people that you're asking in your survey. It goes right here. Now, this critical value of z is exactly the same values as before. If you remember, what we were doing before was the confidence interval for means, for population means. And we used the normal distribution for that when the sample size was large, right? Now, when we do proportions, we're also going to be using the normal distribution. So this guy right here, it comes from the definition of what we call the level of confidence. And we've talked about that many times before. I'm not going to go over it again. Basically, here's a normal distribution, and you say this is z sub c, and this is negative z sub c. In the middle is always 0 for a normal distribution. So if I come down here and I kind of draw some dotted lines, and if I shade this central area here, the area between these boundaries is what we're calling the level of confidence. So it would be 90% level of confidence or 95% level of confidence. So for instance, if I was doing a problem with 95% level of confidence, the area in here would be 0.95. Now you see when you lock down the level of confidence, whether it's 80% or 75% or whatever, you're locking down this area and you're locking down the value of z sub c. They're going to go out or in depending on the level of confidence of your problem. If I'm doing a 99.99% confidence test, then since it's 99% area in here, these are going to be shifted way out and z sub c is going to be bigger. Okay? So because it's a normal distribution and because a normal distribution doesn't ever change, then we were able to construct a table that helped us. So I'm going to say level of confidence. And this is the critical value of z sub c. I've actually given you this table in the last volume before. I'm going to rewrite it here. 0.80, 1.28. 0.85, 1.44. 0.90, 1.645. 0.95, 1.96. 0.98, 2.33, 0.99, 2.575. All right, so if I'm doing a test at a 98% confidence level, then it's 0.98 for my level of confidence, and then the critical value of z that goes into this equation is going to be 2.33. Now, obviously, I've only written some standard common levels of confidence. If I wanted to do 82% level of confidence, then I would have to find the number in here, and I would have to go to the charts and go figure that out. And it all comes down to the definition. The area between here is going to be the level of confidence that you're after. The value of z shifts around with that depending on what this area is. But for most problems, you're going to be doing an 80% or a 90% or a 98% or a 99%. And so you don't really have to calculate that. You just read it off the table and use it. So whenever you get all of this stuff, when you have the sample proportion that you've calculated and you calculate a margin of error that's based heavily on the level of confidence that dictates your critical value of z, then you can construct what we call the confidence interval. And this is the confidence interval for proportions. And what it is you start in the middle. Let me do blue. You start in the middle with your population proportion, and you say that your population proportion's got to be less than your sample proportion plus the margin of error, and it's got to be greater than your sample proportion minus your margin of error. So it's exactly the same thing as before. Before we had mu here, we had the population mean and the sample mean that we were calculating. It's exactly the same concept here. We say that the confidence interval of the population is going to be the sample proportion minus the margin of error, the sample proportion plus the margin of error. This creates a window that we're saying the population proportion falls within. So it's exactly the same before. You use your point estimate is your p hat, which is what you measure, your sample proportion, and you subtract and you add the margin of error from that. So let's get a little bit of practice from that. This isn't going to be a complete problem, but we'll just kind of get our feet wet here, and then we're going to do a few problems here in the next few sections. Let's say we have 13 out of 147 teachers know sign language. Find the margin of error for a 90% confidence interval for the proportion of teachers that know sign language across the country. So you have thousands of teachers, maybe even tens of thousands of teachers or more across the country, and you want to know what percentage of those teachers know sign language. So clearly you can't go measure them all. You can't go survey everybody. It would just take too much time and money. So what you do is you sample. And what they did in this problem is they asked 147 teachers if they knew sign language. Of those 147 teachers, 13 of them said they did know sign language. So now we have some sample data. We think that that's pretty representative of the whole population, but we don't know how accurate it is because it's kind of a small sample, only 147 teachers. And how that relates to the whole body of teachers in the country is a pretty big step. So we want to create a confidence interval, and it's locking down for us that we only care if it's 90% level of confidence. So it doesn't have to be super duper confident or a level of confidence, but it needs to be up there. So how do we do that? Well, you got to go step by step with the problem. You need to write down what you know, and you need to make sure you understand what the problem's asking you to do. So what we're saying is the level of confidence in this problem is 90%. 90%. So whenever you're doing something with proportions like this, you need to say, what is this part telling me? Well, what it's telling me is really, if I were going to do the whole thing manually, it would say that the area here is the level of confidence. It's 0.9. So if I go look at my chart in the back of my book, and if I lock down the area here, I should be able to find the value of z here and here that make this 0.9 in the middle. But see, I've already done that work for you and given that to you here because we've constructed this table. So if the level of confidence is 0.9, what it's telling you is that this value of z is 1.645 and this value of c is negative 1.645. And if you look at a normal distribution between those numbers, the area between is exactly 0.9. That's how this table is constructed. So the critical value of z is 1.645. So that's important. 1.645. Okay? All right, so we have the z sub c. And then we go and say, well, how do we create or calculate the margin of error? That's given to us right here. The margin of error for proportions, for confidence intervals of proportions, is the critical value of z times the square root of p hat 1 minus p hat over n. All right, so I know what this critical value of z is. I know what n is because I know that I've asked 147 teachers this question. That's the number of teachers I've sampled. But I don't really know what p hat is. That's not usually going to be given to you in the problem, but it's always possible for you to find out what p hat is. And the way for you to do that is just to say, well, p hat is the sample proportion of teachers that know sign language. So really all it is 13 teachers out of 147. It's a fraction, right? And when you do this, you get 0.088. So the way you express it as a decimal is 0.088, but really if you shift the decimal 2 spots to the right, it'll be 8.8%. These are kind of the same exact thing. Whether you represent it as 0.088 or 8.8%, that is the sample proportion. Now when you're dealing with the equation and you're actually doing calculations with p hat, you never want to use the percentage. You want to use the raw decimal. That's just a rule of thumb. All right, so now we can calculate the margin of error. Z sub c, we said for this level of confidence, is 1.645. And then under the radical here, under the square root, I have p hat, which is 0.088. And then I have 1 minus p hat, 1 minus 0.088. And all of this is under the square root sign. And then also under here I have n, but I know that n is 147 people. That's how many teachers I actually asked here. Okay? And so what I end up getting is 1.645. Now if I take 1 minus 0.088 and I multiply by 0.088 and I divide by 147, this will give me a number, and then I take the square root of all of that stuff at the end, I would get 0.023. All right, so now I have two numbers to multiply. The margin of error when you multiply those is 0.038. This is how you express it as a decimal, but since this is all about proportions, you can also express it as a percentage, 3.8%, because you can shift you multiply by 100, you shift the decimal 2 spots, it becomes 3.8%. So this particular question didn't actually ask you to calculate the confidence interval. This question said find the margin of error for the confidence interval at 90%. For the number of teachers nationwide who know sign language. And we're saying the margin of error is 3.8%. So what we're basically saying is that we did our sampling, we got basically what we got from our sampling when we asked 147 teachers is that 8.8% of them knew sign language. But we know that's not really true for the whole population. There has to be an error associated with this sampling estimate, and now we know that that error basically is plus or minus 3.8%. If we were going to calculate a confidence interval, the lower bound would be 8.8 minus 3.8. That would be the lower percentage. And the upper bound would be 8.8% plus 3.8%. Remember, what you sample, what you measure is right in the middle of your confidence interval. The margin of error is going to be minus and plus. That creates a window. We're saying the population proportion falls in the middle of that. We're going to be doing a lot more problems in a few sections coming up. I know this is kind of a long section. It's kind of getting the gears turning and the juices flowing for confidence intervals. For proportions. But you just need to know that the concept's almost exactly the same as what we've done before. There is a margin of error that's associated with this, and you're allowed to use the normal distribution for these types of problems, for proportions, for population proportion problems. You need to look up here from your level of confidence, get your critical value of z, calculate the margin of error, and then your sample estimate, your point estimate, is going to be right in the middle of your confidence interval as we've done all along. So follow me on to the next section. We're going to do a few more problems dealing with population proportions and confidence intervals. And then we're going to get into hypothesis testing, and you're going to figure out, after seeing these equations over and over, that the concept is very similar. Obviously, hypothesis testing is different, but the overall concept, there are a lot of similarities. So make sure you understand this and follow me on to the next section in this course. Learn anything at mathandscience.com.